Hello everyone. In this video, we are going to solve a question that came in IIT JEE 2003. Okay. Since then, this question has also appeared in various entrance exams like JEE Main and various state level entrance exams in different forms. Okay. Even very recently in 2019, a modified version of this question appeared in JEE Main 2019. Okay. So I'll tell you how to crack this question. I'll also tell you how to do this question in 10 different ways. So you must be wondering, sir, why do you complicate stuff? Why do you give us 10 different ways to do this question? Why don't you just tell us the shortest way to do this? Okay, but here is the trick. Here is the catch. When you're actually appearing in an exam, during an exam, how do you approach a problem? In general, you know that a math problem can be approached in multiple ways. Most of the time, a problem can be done in different ways. Okay, you are always looking for the shortest way to crack it. That is true. But during an exam, how do you do it? Do you plan to do it in the shortest way? It is not always possible because you don't have that kind of a time to think and come up with the shortest way to do the question. How will you do the problem? You will do in a way which strikes you first. Okay, whatever comes to your mind first, and that will be the approach you will be taking to solve a particular problem. Okay, so that is one thing. And secondly, by solving this question in 10 different ways, I'll cover almost all the concepts that come in the chapter complex numbers. Okay, and if you want more similar videos, I am planning to do more similar videos. If you want to get access to those videos right now, go to this channel and subscribe the channel. Also make sure that you click on the bell icon and enable all notifications. So let's go to this question. Okay, quickly read the question. The question says, if z is a complex number satisfying mod z is equal to 1 and z is not equal to minus 1, then the real part of omega equal to z minus 1 by z plus 1 is. Okay, so going through this question, going through different ways, I'll tell you what all things will come to your mind and how you can come and get to an answer by the different approaches that might strike you during an exam. Okay, so stay tuned and watch till the end. If you're looking for the shortest solution to the problem, watch till the end, because in the end of the video, towards the last part of the video, I'll reveal how this can be solved in 2 seconds. Okay, just like that. Fine. So stay tuned. I am discussing all this because I told you now, using this question, I want to tell you the multiple approaches by which you can crack a question. So first of all, so we have a complex number z and modulus of z is equal to 1 and z is not equal to minus 1. Why is z not equal to minus 1? Because z is equal to minus 1 is going to put you in trouble. It will make the denominator 0. So forget about z is equal to minus 1, and excluding that point, you have to find the real part of the omega, and omega is nothing but z minus 1 by z plus 1. So first thing that comes to your mind, okay, for most of the people, the first thing that comes to the mind is putting z is equal to x plus iy. Okay, represent our z in terms of rectangular coordinates. That is the first thing that comes to your mind. So your omega is going to be, put z is equal to x plus iy. This is x plus iy minus 1 by x plus iy plus 1. Okay, now we have to find the real part of this complex number. This is not in the standard form. So before writing it in the standard form, let's rewrite and arrange the real parts and imaginary parts. So this is x minus 1 plus iy divided by x plus 1 plus iy. Okay, you have to remember one thing. We have substituted z is equal to x plus iy, and in the question it is given that mod z is equal to 1 and mod z is nothing but root over x square plus y square. So we have root over x square plus y square is equal to 1, which also means that x squared plus y squared is equal to 1. Okay, we have this fact ready here. Okay, now this complex number is not in the standard form, it's not in the a plus ib form. You have to rewrite in the a plus ib form. For that, you have to multiply with the conjugate of the denominator on both numerator and denominator. Doing so, it will make sure that the denominator of this expression becomes a real number. Okay, when you multiply a complex number by its conjugate, you get modulus square of the complex number. So the in next step, what I'm going to do is, this is x minus 1 plus iy divided by x plus 1 plus iy. So I'm going to multiply both numerator and denominator with the conjugate of the denominator, that will be x plus 1 minus iy divided by x plus 1 minus iy. Okay, that makes sense. Now look at our expression. Okay, by the way, we don't have to write the entire expression, we just need to take real part of omega, right? How will you get the real part? In the denominator, the entire expression is going to be a purely real number, so it will be, this is of the form a plus ib into a minus ib, so that is going to be x plus 1 the whole square plus y square. That's all right. And in the numerator, it's going to be a complex number, you just need to pick the real part alone. So how will you get the real part? You multiply x minus 1 into x plus 1, what do you have? You have x squared minus 1. Okay, you multiply iy with minus iy, I into I is minus 1, I into minus I is plus 1, so that becomes y squared. And now look at this, we have x squared plus y squared minus 1, and our x squared plus y squared is equal to 1, so this answer is nothing but 0. Okay, don't worry about the denominator, the numerator becomes 0, so our answer is 0. Okay. Okay, this is a very easy way. This must be the most straightforward way that might come to your mind, maybe during an exam or something. Okay. Now, let's see how this can be done using another method. Okay. So, in the previous method, we were using a rectangular coordinate. Not everybody prefers to use rectangular coordinates. Sometimes you might want to use polar coordinates. Okay, so in this case, I'm going to put z is equal to r into cos theta plus I sin theta. Okay, and of course, mod z is 1 and mod z is nothing but our r. So this is cos theta plus I sin theta. Now let's follow the previous approach. Instead of x plus iy, we have cos theta plus I sin theta. Earlier we had x squared plus y squared is equal to 1 condition. Now that condition is inherent in this equation, it's inbuilt. This, if this is x plus iy, x squared plus y squared is already 1. We don't have to write a separate expression. Okay, so suppose if you think that maybe if it strikes you that polar expression is going to help you, so you might start with this method, and let's see how this can be done using this approach. So our omega is going to be z minus 1 by z plus 1 is cos theta plus I sin theta minus 1 by cos theta plus I sin theta plus 1. Alright, now again, just like we did in the previous part, we have to rearrange it. Cos theta minus 1 plus I sin theta divided by cos theta plus 1 plus I sin theta. Okay, and we need to multiply with the conjugate of the denominator on both numerator and denominator to extract its real part and imaginary part. So this becomes cos theta plus 1 minus I sin theta divided by cos theta plus 1 minus I sin theta. Now you just need to take the real part. Real part of omega is going to be, okay, in the denominator we have some expression, don't worry about it for the time being. let's take a look at the real part. We have cos theta minus 1 into cos theta plus 1, that is cos square theta minus 1. We have I sin theta into minus sin theta. Remember, I'm just writing the real part. I'm not writing the imaginary part. We just need to write the real part. So that is going to be plus sin square theta. And now look at this. Cos square theta plus sin square theta minus 1 is going to be 0. So our answer is 0 again. Cool? Yes. Let's go to the next approach. Okay. Now, in this approach, I am going to use the same polar form, but the algebraic manipulation will be slightly different. Okay, let's see how the manipulation can be done in a different way. So, put z is equal to cos theta plus I sin theta, just like in the previous case. Put z is equal to cos theta plus I sin theta as in the previous case. Now, your omega is going to be cos theta plus I sin theta minus 1 divided by cos theta plus I sin theta plus 1. Okay. So, this is going to be cos theta minus 1 plus I sin theta divided by cos theta plus 1 plus I sin theta. Now, suppose you are good at trigonometry. So, instead of resorting to some algebraic manipulation, let's go with trigonometric manipulations. So, cos theta minus 1. We know 1 minus cos theta is 2 sin square theta by 2. So, cos theta minus 1 is going to be minus 2 sin square theta by 2. Plus I times sin theta is 2 sin theta by 2 cos theta by 2. Right? And in the denominator, cos theta plus 1 is going to be 2 cos square theta by 2 plus I times 2 sin theta by 2 into cos theta by 2. Alright? Yeah. Now, you can easily cancel off 2 in both numerator and denominator. Also in the numerator, I'm going to take this sin theta by 2 out. So, what do we have remaining? We have minus sin theta by 2 plus I cos theta by 2 divided by, we have cos theta by 2 into cos theta by 2 plus I cos theta by, I sin theta by 2, right? Now, look at this expression. We have cos theta by 2 plus I sin theta by 2 here. We have a very similar expression here, but it's slightly different. But if you observe that, if you can take I outside from the entire expression, if you can take I out, okay, from minus 1, if you take I out, what is going to be left? It will be I. Okay, so take I out, and it is going to be I sin theta by 2 into, and this expression is I sin theta by 2 plus cos theta by 2 divided by cos theta by 2 into cos theta by 2 plus I sin theta by 2. Now, these two expressions gets cancelled off. Okay, this is cos theta by 2 plus I sin theta by 2. This is again cos theta by 2 plus I sin theta by 2. Now, look at this expression. This becomes I tan theta by 2, which is a purely imaginary number. Okay, your omega happens to be a purely imaginary number. So, what's the real part? Real part is 0. Right? So, that was our third method. Now, in the next method, suppose, okay, we have already used rectangular coordinates, we have used polar coordinates. In the next method, I'm going to use Euler's form. Okay, so for Z, I'm going to put Euler's form as r e raised to I theta. Okay, now let's see how this manipulation can be done. So here r is 1, so it is nothing but e raised to I theta. So our w is nothing but e raised to I theta minus 1 by e raised to I theta plus 1. Okay. Now to simplify this expression, what I am going to do is I'm going to multiply the numerator and denominator with e raised to minus I theta by 2. I'll tell you why this will work. We'll see soon how this will work, how this will help us. So when you multiply the numerator and denominator with e raised to minus I theta by 2, see what happens? The numerator expression becomes e raised to I theta by 2 minus e raised to minus I theta by 2 divided by denominator we have e raised to I theta by 2 plus e raised to minus I theta by 2. Now look at the numerator and denominator. They have come in such a nice way, nice form. This is very familiar to us. Okay, this has come to us in a very in a favorite way, because see, e raised to I theta plus e raised to minus I theta, we know this is the real parts gets added up, imaginary parts gets cancelled off. This is 2 cos theta, and e raised to I theta minus e raised to minus I theta is 2i sin theta. Okay, so in this case the numerator is 2i sin theta by 2, denominator is 2 cos theta by 2. So 2 gets cancelled. This is I tan theta by 2, just like in the previous case. This is a purely imaginary number, hence the real part is 0. Cool? So that was our fourth way of doing it. Now, somebody might be thinking, why give a substitution at all? Why don't you just deal with z itself? Okay. So we have omega is equal to z minus 1 by z plus 1. To figure out things, I'm going to multiply with the conjugate of the denominator. So z plus 1 we have in the denominator, I'm going to multiply with the conjugate of z plus 1. Remember, conjugate of z1 plus z2 is going to be z1 conjugate plus z2 conjugate. So conjugate of z plus 1 will be z conjugate plus 1 conjugate. 1 is a real number, so 1 conjugate is 1 itself. So this is going to be z conjugate plus 1 by z conjugate plus 1. Alright. And in the denominator we have z plus 1 into its conjugate. So it is going to be mod z plus 1 the whole square. Why? Because it's z plus 1 into its conjugate. In the numerator we have z bar minus z bar plus z minus 1. Now this z bar is nothing but mod z square, and it is given as 1. So these two gets cancelled off. Okay, and in the numerator we have z minus z conjugate divided by mod z plus 1 the whole square. And we know what z minus z conjugate is. Z is equal to x plus iy. Z conjugate is x minus iy. Z minus z conjugate is going to give you 2iy, which is nothing but 2i times imaginary part of z. Okay, 2i times imaginary part of z. So this is going to be I times 2 times imaginary part of z by modulus of z plus 1 the whole square. So this is a real quantity. Why? Because imaginary part of a complex number is real. This is also a real number. So we are left with I multiplying a real quantity which is purely imaginary. So the real part of this quantity is 0 because it's purely imaginary. That was our fifth way of doing it. Okay. Now let's move on to the next way. Okay, now look at this. We have mod z is equal to 1 and w is equal to z minus 1 by z plus 1. What we need is real part of omega. So there is a standard definition for real part of omega in terms of omega and omega conjugate. It is half of omega plus omega conjugates, because omega plus omega conjugate is going to give you 2 times real part of omega. complex number plus its conjugate is 2 times real part of the complex number. So half of omega plus omega conjugate. So this is going to be half of z minus 1 by z plus 1 plus z conjugate plus 1 by, z conjugate minus 1 by z conjugate plus 1. Now to simplify this expression, let's simplify this expression. So denominator is going to be z plus 1 into its conjugate is mod z plus 1 the whole square. Okay, it's going to be a big expression in the numerator. It's going to be a big expression. See, we have z minus 1 multiplying with z bar plus 1. So it will be z bar plus z minus z bar minus 1. And next, we have these two terms multiplying. So we have z bar, then it's minus z, then we have plus z bar, then we have minus 1. Now see this, z bar is mod z square, which is 1, gets cancelled with 1. Z bar is mod z square, cancels with 1. And what is remaining is, and see this, z and minus z gets cancelled off, minus z bar and z bar gets cancelled off. So everything goes away. Ultimately, what we have found out is this is real part of omega and real part of omega comes out to be 0. That is another way to approach this question. Okay. That was the sixth way. So in the seventh method, so far we were thinking from the perspective of omega. Now let's think from the perspective of z. Okay. So in this question, we have w is equal to z minus 1 by z plus 1. I am going to find z in terms of w. I am going to find z in terms of w. Okay. Why? Because I am going to think from the perspective of z. Z is telling me that my modulus is 1. So I am going to find z and put mod z is equal to 1. That is my approach. So you can find z in terms of omega by two ways. Either cross multiply and simplify or use componendo and dividendo. Okay. So if I use componendo and dividendo, omega plus 1 by omega minus 1 is going to be z minus 1 plus z plus 1 by z minus 1 minus of z plus 1. So we have 2z divided by minus 2. So ultimately our z is 1 plus omega by 1 minus omega. Z is 1 plus omega by 1 minus omega. So we have written z in terms of omega. Now what will I do? I am going to put mod z is equal to 1. So modulus of 1 plus omega by 1 minus omega is equal to 1. Okay. Now this means modulus of 1 plus omega is equal to modulus of 1 minus omega. I don't like modulus. To get rid of modulus, you have to multiply, you have to take the square. Now this is modulus square of a complex number. This is modulus square of a complex number. What is modulus square of a complex number? It's nothing but complex number into its conjugate. So this is going to be 1 plus omega into its conjugates. 1 plus omega conjugate. This will be 1 minus omega into its conjugate, 1 minus omega conjugate. So let's simplify and see what happens. So it will be 1 plus omega conjugate plus modulus of omega square. Why? Because omega into omega conjugate. 1 minus omega conjugate plus modulus of omega square. So 1 gets cancelled. Omega square, modulus omega square gets cancelled. We have 2 times omega plus omega conjugate is equal to 0. And this omega plus omega conjugate, we already know it is 2 times real part of omega. So we have 4 times real part of omega is equal to 0. So we have real part of omega equal to 0. That was a 7th way of doing it. Now let's go to the next way. Okay. In this approach, I'm going to think from the perspective of z again, but instead of doing the algebra, I'll do it geometrically. See, we have w is equal to z minus 1 by z plus 1. Okay, we have already seen that this can be written as z is equal to 1 plus omega by 1 minus omega. Okay, and we have mod z is equal to 1. So this is going to be modulus of 1 plus omega is equal to modulus of 1 minus omega, or rather it is modulus of omega plus 1 is equal to modulus of omega minus 1. Now let's try to think geometrically. Okay, we know that modulus of z1 minus z2 is going to give me the distance between two complex numbers z1 and z2. So this is nothing but distance between omega and minus 1, and this is nothing but distance between omega and 1. Our expression says that distance between omega and minus 1 is same as distance between omega and 1. Now if you try to represent it geometrically, we have the complex number minus 1 here, we have the complex number 1 here, and our omega is such that it's equidistant from both minus 1 and 1, and we know that it is going to be nothing but the set of all points. Omega will lie on the perpendicular bisector of the line segment joining minus 1 and 1. So our omegas will lie here. Okay, condition. What is the condition? We have distance from omega to minus 1 is same as distance of omega to plus 1. So set of all omega satisfying this condition is going to lie on the perpendicular bisector joining minus 1 and 1. So this is nothing but our y-axis. Okay, so which means omega is lying on imaginary axis, omega is purely imaginary, real part of omega is 0. Okay, so if you want to generalize this expression, always remember, somebody tells you modulus of z minus z1 is equal to modulus of z minus z2, z1 and z2 are two fixed points, then the locus of z is going to be the perpendicular bisector of the line segment joining z1 and z2, or z is going to lie here on the perpendicular bisector, because these two distance will be always same. When you take any point on this dotted line, its distance to z1 and z2 will always be the same. Okay, that was our 8th way of doing. Now comes to the 9th method. So in this method, I'm going to drop complete algebra. I'm going to represent everything geometrically. Okay, now we have z is a complex number satisfying mod z is equal to 1. What does this mean? It means that mod z is equal to 1 means that distance of z from origin is 1 unit. So it is going to represent a circle centered at origin having radius 1 unit. So our z is going to lie on a unit circle. Z is any point on the unit circle, and this is our 1 and this is our complex number minus 1. Suppose we take z here. Now in this question, I'm going to look at the argument of this complex number. Okay, what will be argument of z minus 1 by z plus 1? We know that argument of z1 by z2 is nothing but argument of z minus 1 minus argument of z plus 1. Okay, now what does argument of z minus 1 give me? Okay, for that you should know that argument of z1 minus z2 gives the angle made by ray joining z2 to z1 with the positive direction of x-axis. Argument of z1 minus z2 is going to give you the angle made by the ray joining z2 to z1 with the positive direction of x-axis. Argument of z is nothing but the angle made by the ray joining origin to z with the positive direction of x-axis. So this angle, argument of z minus 1 is going to be the angle made by ray joining 1 to z with the positive direction of x-axis. So let's call this theta 1. And similarly, argument of z plus 1 is going to be the angle made by the ray joining minus 1 to z with the positive direction of x-axis. So let's call this theta 2. And in this case, it is nothing but theta 1 minus theta 2. From the figure, it's clear that this is a semicircle. This angle is nothing but theta 2 minus theta 1, which is pi by 2. So we have taken argument of this quantity, argument of omega, and argument of omega comes out to be pi by 2, which means omega is a purely imaginary number. Okay. So if we had taken z on the lower semicircle, okay, lower semicircle, this would have been minus pi by 2. Even that, in that case, this argument of omega is going to be minus pi by 2. So it is again a purely imaginary number, right? Okay. Now I'll just give a generalized result. If you have a complex number z1 here, this is z2 here, suppose this is z0, okay, this angle is alpha, okay, argument of z2 minus z0 by z1 minus z0 is going to be alpha, okay. So if you know this result, directly drawing this figure, you can figure out that this argument of this quantity is nothing but pi by 2. Or if you take z here, it is minus pi by 2. So this method, if you know the geometry part well, use this, you can do it in 10 seconds. But ultimately, the easiest way to do this in an exam, especially in a multiple choice question, is see this question. They have given that z is not equal to minus 1. That is well and fine, because you don't want to do illegal things by putting 0 in the denominator. But as long as, see, mod z is equal to 1. So you can simply put z is equal to 1 and verify the options. You simply put z is equal to 1 because it satisfies all the conditions. Z is not equal to minus 1 and mod z is equal to 1. So simply put z is equal to 1 and this expression disappears. This becomes 0. This expression becomes 0. And see, none of the other options match. So when the complex number is 0, real part is 0, imaginary part is 0, none of the expressions match except this one. Okay. So we have seen so many methods, but ultimately it's a matter of 2 seconds if you can observe the question and observe the options very well. Okay. So why am I telling you all these methods? Because I told you in an exam, the best way to approach a problem is using the first thing that comes to your mind, not using the easiest way. Okay. So depending on the insights you have, depending on the practice you have had, you will be able to do it in the easiest way possible. Okay. And also, apart from that, I've told you all this different method because all these are standard tricks which can be used to solve other problems from the geometry part as well as the algebra part of the complex numbers. So if you like this video, please stay tuned for more videos and do share this with your friends as well. Thank you.